Hello friends, welcome back to my channel Chemistry Unplugged. Today we will learn about acid-base theories and factors affecting acidic and basic nature of organic molecule. We will take lots of examples and you can follow me on Unacademy using my name Nidhi Verma, where I will upload complete courses of these topics. So let's start the video. There are three theories which can define acidic and basic nature of organic molecules. First is Arrhenius, second Bronsted-Lowry Theory, third is Lewis Theory. And among them, Bronsted-Lowry Theory and Lewis theories are very important. According to the Arrhenius theory, acid generates proton and base generates OH-. Suppose in case of NaOH and HCl reaction, there is the formation of NaCl and water. So in this reaction, NaOH is acting as a base because it is generating OH- and HCl is acting as a acid and it generates H+. So there is the formation of salt plus water, and this reaction is known as neutralization. We all know about this. Second theory is Bronsted-Lowry Theory. According to this theory, acids are the substances which generate H+, and base are the substances which accept proton. For example, HCl is a gas, and when it is a gas, it is not acid or base. But because it is not generating, it is not present in the form of H+ and Cl-. But when we dissolve it in the water, then it will dissociate to form H+ and Cl-. This H+ will combine with water to form H3O+, known as hydronium ion. And HCl is acidic because of the presence of hydronium ion. Then third theory is the Lewis theory. According to the Lewis theory, acids accepts electron while base donates electrons. So Lewis theory is somewhat similar to the Bronsted-Lowry theory because when acid generates proton, it is removing H+ from it, so there is addition of electron on the central atom. And in case of base, because it is accepting H+, according to the Bronsted-Lowry theory, and in this way they are donating their electrons to the H+. So Bronsted-Lowry theory and Lewis theory are almost same, but their point of view is different. But Arrhenius theory is completely failed because all the acids and base molecules do not have OH and H+ to donate or accept. In some cases like BF3 and AlCl3, where we do not have any H+, then we can explain their acidity or basicity using Lewis theory only. So Bronsted-Lowry theory and Lewis theory are very important. And in this video, we will discuss about Bronsted-Lowry theory, and we will discuss in next video about Lewis theory. So suppose we have an acid, and when we dissolve it in the water, we have H3O+ and A-. So because Ha is donating H+, it is a proton donor, therefore it is acting as an acid. And water, which is accepting protons, is a proton acceptor, and therefore it is known as base. So when Ha donates its proton, it will be converted into A-. So it is known as its conjugate base. And H3O+, which is formed by the acceptance of proton by water molecule, therefore it is a conjugate acid of base water. So this reaction is a reversible reaction, and the Ka is the equilibrium of this reaction. We can write it down like this: H3O+ A- upon Ha. We will not consider water because it is in large quantity and its concentration is not changed so much. It will remain almost constant. So if we want to calculate pK of this reaction, we can use minus log Ka. And if a organic molecule has lower value of pK, it will be highly acidic in nature. So first point to be remembered is that stronger the acid, weaker will be its conjugate base. There is an inverse relationship between them. If acid is strong, its conjugate base will be weaker in basic nature. Okay, so it will be more stable because it is not participating in the reaction as a base, therefore it will be more stable in nature. And weaker the acid, stronger will be its conjugate base. So there is a vice versa relationship. Stronger means it will be less stable because it is acting as a strong base and it will easily participate in the reactions, therefore it will be less stable in nature. So what are the factors affecting the strength of an acid? First is the strength of Ha bond. Suppose we have Hi, HBr, HCl and HF and we want to calculate the acidic strength of them. So in this case, because the bond distance between the bond length of H and A is the highest, because proton is has a small orbital and iodine is a large atom and it has a bigger atomic orbital. So the bond length between H and I is large. When the bond length is large, the strength will be low, and HF has lowest bond length because atomic orbitals of H and F are almost similar in size. So it has smallest bond length. So down the group, the bond length increases and the bond strength decreases. So when we have lower bond length means that HX or the HI bond can easily be broken as compared to HF bond. When we can easily break HI bond means we can generate H plus in larger amount as compared to HF. So HI will be a stronger acid as compared to HF. So the order of strength will be this. Most acidic is HI, then HBr, HCl and HF will be least acidic in nature. Second factor is electronegativity of A. A is the conjugate base formed after the removal of proton. So if A is more electronegative, then it can easily hold negative charge with it and the conjugate base form will be more stable. If it is more stable, then acid will be stronger in nature. Suppose we have methane, ammonia, water and HF. So we want to calculate their acidic strength order. So first we will determine what are their conjugate base. So in case of CH4, it will become CH3 minus. For ammonia we have NH2 minus. For water we have OH minus. HF will form F minus. So among them, the atom which contains negative charge is central atom is carbon, nitrogen, oxygen and fluorine. And fluorine has highest electronegativity. So order of electronegativity will be fluorine, then oxygen, then nitrogen and last is carbon. So fluorine can easily hold its electrons with it and it will be more stable conjugate base. So the order of acidity will be HF, then H2O, NH3 and last for the CH4. Third is stabilization of A. Stabilization of conjugate base formed. This stabilization can be done by conjugation and delocalization. For example, we have 4 acids HClO, HClO2, HClO3 and HClO4 and we want to compare their acidic strengths. So first we will form their conjugate base. This will be ClO minus, ClO2, ClO3 minus, ClO2 minus, ClO3 minus and ClO4 minus. So in all the cases, the atom which is carrying negative charge is oxygen, which is same. So we cannot determine by this their acidity using other factors. So first we will find out that this negative charge is delocalized over only one oxygen. In case of ClO2, it is delocalized over 2. In case of ClO3, it is 3 and ClO4, in case of ClO4 minus, it is delocalized over 4 oxygen atom. Like this one, this is ClO4 minus. So if we delocalized this negative charge, it can be placed here or we can have a number of structures. So in this way, ClO4 minus is more stable because we have 4 canonical forms on which the negative charge can delocalized. So because it is highly stable, therefore HClO4 has highest acidic strength. Then fourth is the nature of solvent. So if we dissolve an acid in a solvent, suppose we are taking here water. So in this case, this is acting as an acid because it is donating proton, and solvent is acting as a base because it is accepting protons. So if it is a strong base, then it can easily remove proton from the acid. So the strength of acid will be high. It can easily break Ha bond. So we have larger amount of H plus, and in this way its dissociation is high, the value of alpha is high, therefore it is acting as a strong acid. And if the base is weak, then the acidic nature of the acid will also decrease because it is not able to abstract protons from the acid. So in this case we are using water, and this water forms hydronium ion when it combines with the protons of acid, which is very stable in nature. So if I am using water as a solvent for different acids, like I am using for HCl, then it will form hydronium ion. Same is the case for other acids also. So when I am using water, the dissociation of acid is complete. It will be completely, almost fully dissociated when I am using water as a solvent, because the hydronium ion formed are very stable in nature. Therefore, for all the acids HCl, H2SO4 and HClO4 minus, strong acids, the degree of dissociation is almost 1. Means they are fully dissociated. So we cannot compare their acidity using water as a solvent. Water is limiting their acidity. Therefore, water is acting as a leveling solvent, and this is known as leveling effect of water, because degree of dissociation or the acidity of all the acids are same. We cannot compare their acidity. Therefore, this is called as leveling effect of water. Now we will take various groups attached with organic molecule to define their acidity or basicity. And another important factor which is governing the acidity or basicity of the molecules is inductive factor. So suppose we have acetic acid and we are replacing one hydrogen of acetic acid with fluorine. So in this case it will become CH2FCOH, then CHF2COH, and when we replace all, it will become CF3COOH. And we all know that fluorine has minus I effect. It will attract electrons towards it. In this way, the proton can easily be removed from the molecule, and it is acting as a strong acid. The minus I effect showing groups are R3N+, NO2, halogens, nitrile group, SO2R group, CO2R. All of them show the minus I effect. So when they are attached with organic molecule, their acidic nature will increase. Another possibility is this: how close these negative I effect causing groups to the proton. So if they are close to it, then the acidity will increase, and if they are far, then acidity will be decreased. Next examples are phenols. So this is the molecule of phenol. When we remove one proton from it, it will form its conjugate base, and this conjugate base is very stable in nature because its negative charge is delocalized over the benzene ring. So when the conjugate base is stable, means acid has higher acidic strength. So phenols are the good acids in nature. And if we compare it with aliphatic alcohols, ROH, then there is formation of RO minus as a conjugate base, and its negative charge is not delocalized or conjugated, so it is less stable as compared to phenoxides. So phenols are the good acids as compared to alcohols. And if I connect the alcohol with a electron withdrawing group like NO2, then its acidic strength is, then after the proton removal, its conjugate base will be this. So, and it has, when nitro group is present at para position, it has electron withdrawing mesomeric effect, means minus M effect. So the electrons present on oxygen atom can further be delocalized. So it is a better way of delocalization as compared to simple phenol. it means its delocalization is increased, it will be more stable, its conjugate base is more stable, means para-nitrophenol is more acidic as compared to phenol. And this mesomeric effect is pronounced for the para and ortho position. Therefore, para and orthonitrophenols are more acidic as compared to meta. At meta position, there is no mesomeric effect. Therefore, it is least acidic in nature. And because in case of ortho substituted nitrophenol, it is also showing minus I effect. Therefore, acidic strength is somewhat decreased as compared to para-nitrophenol. Then we will take carboxylic acids. We all know that carboxylic acids are acidic in nature, and aromatic carboxylic acids are also very acidic in nature, because when there is formation of a conjugate base, their conjugate base is stabilized by delocalization. Therefore, they are more acidic in nature. And if we substitute a nitro group at para position, then this nitro group will show negative I effect. And because of this negative I effect, when nitro group is close to COO minus, then the negative I effect will be more pronounced. Therefore, ortho-nitrobenzoic acid will be more acidic as compared to para substituted. These are the groups which can show mesomeric effect, plus mesomeric effect, and minus I effect. Because of the lone pair present on these atoms, oxygen and halogens, they can show plus am effect. So when we substitute benzoic acid with these group, then what will happen? In case of ortho and para substituted, we have plus am effect, because at meta position there is no mesomeric effect. Therefore, when we substitute them at ortho and meta position, they will show plus am effect. OH, suppose we substitute OH at para position, then it is acting as a plus am effect, and it will donate electrons to the COH minus, and when the negative charge carrying moiety is given more electron, it will become less stable. So when we substitute OH at meta position, it will not show plus am effect, because at meta position it is not possible. So it is only showing minus I effect. So meta substitute is more acidic as compared to para, because at para position it is showing plus am effect, which is decreasing negative charge of conjugate base. Therefore, it is less stable in nature, and meta position is more stable in nature. Therefore, meta substituted benzoic acid is more acidic in nature. But when we substitute OH at ortho position, then although it is showing plus am effect, but it will show hydrogen bonding with the oxygen atom of carboxylic group, and in this way it will become more stable, most stable in nature. Therefore, ortho hydroxybenzoic acid is the most acidic in nature, because its conjugate base is stabilized by hydrogen bonding. So if we substitute benzoic acid with methoxy group, then it will show plus am effect when it is present at para and ortho position, and at meta position it will show only minus I effect. So the order of strength will be highest or almost similar for the ortho and meta position, and lowest for the para position. It is similar to hydroxy substituted benzoic acid, but because there is no hydrogen bonding, therefore ortho methoxy benzoic acid is not most stable in nature. Then second is dicarboxylic acids. Dicarboxylic acids are more acidic as compared to monocarboxylic acid, because they have two carboxylic group. In this way, they have more acidic nature. So formic acid is less acidic as compared to oxalic acid. Acetic acid is less acidic as compared to acid. And if I compare benzoic acid with C6H4COH whole twice, then it will be more acidic in nature. Benzoic acid will be less acidic. So now I will compare the acidic strength of all of them. So the group which is carrying two carboxylic group will be more stable in nature. Therefore, among them, group second will be most acidic in nature because it do not have any methyl group which will show plus I effect. So, and it only has COOH groups. So it is most acidic in nature. The next is 4th, then 6th, then the order is for 1 and 5, and last is the 3. Then compare the acidic strength of malic acid and fumaric acid. They structure are almost same, but they are diastereomers of each other because one is cis, another is trans. So what is the effect of their geometry on their acidic nature? So first we will form their conjugate base. So after formation of conjugate base, this hydrogen on one carboxylic acid can show hydrogen bonding with the oxygen of other. So it is more stable in nature because of hydrogen bonding, or it gets stabilized by hydrogen bonding. But in case of fumaric acid, it is hydrogen bonding is not possible because two carboxylic groups are in the different directions. So malic acid is more acidic as compared to fumaric acid. Then we will discuss about bases. So we can define base using pKb. In case of acids, we use the term pKa, and for the bases, we can use pKb. But in general, pKa is also used for bases. So how it is possible? pKa is not the term used for a base. It is actually for its conjugate acid. When a base combined with, suppose, water, or we dissolve a base in a water, then there is formation of its conjugate base and OH minus. So the value of pKa is for the conjugate acid of base formed. So if the value of pKa is low, then acidic strength of conjugate acid will be high, so base will be weak in nature. And if the value of pKa is high, then conjugate acid will be lower acidic, or its acidic strength will be low and the base will be strong base. So for the bases, the value of pKa should be high. For their more basic strength, the value of pKa should be high. The next is amines. So now we will compare the acidic basic strength of amines when we substitute them with methyl group. If I place one methyl group, the plus I effect will be low. And when we increase the number of methyl groups, then the plus I effect will increase. So when there is increase in plus I effect, the electron strength on nitrogen will be high. So in that case, their basic strength should be high. But the acidic strength of amines is not only governed by plus I effect, it is also influenced by the solvation effect of solvent. So the order of basicity will be secondary, then primary, third is tertiary, and last for ammonia. It is for methyl substituted amine. So you can simply remember this using a term is SUBTA, is for methyl substituted amines. And for ethyl substituted amines, the order will be STPA. This order is due to the overall effect of plus I effect and solvation effect. Next we will take aniline. So in case of aniline, the lone pair of electron present on nitrogen is the part of the benzene ring. It is delocalized. It can delocalize over the benzene ring. Okay. So these electrons are not free to be combined with proton easily. So the basic strength of aniline is low as compared to the aliphatic amines. They are weak base in nature, but when they are acting as an acid, means when we remove a proton from them, the conjugate base formed get stabilized by delocalization. The negative charge on NH group will be stabilized by delocalization. Therefore, their conjugate base is stable in nature, means they are good acids as compared to base. And if I substitute aniline with nitro group, then because of the minus M and minus I effect, they will show their basic strength. So at the ortho and para position, there is only minus I and minus M effect, but at meta position we have only minus I effect. So because of the minus M effect, they can attract electrons towards nitro group attracts electrons towards it, so the electrons is less available on NH2 group. So in this way, the basic strength of aniline is further decreased at ortho and para position. So the order of basic nature will be maximum for meta, then for ortho, and last for para, because at para position mesomeric effect is maximum. And if I am using methoxy group which is showing plus M effect and minus I effect, then what will be the order of their basic strength? The basicity order is maximum for para position, because the plus M effect is maximum at para position, then ortho, and last for the meta position, because at meta position we have only minus I effect. So because of minus I effect, there is less availability of electron on NH2 group. The next group is amide. So we want to check amides are acid or basic in nature. So first we will draw its structure. So amide can exist in these two forms. So if I provide a proton in the system, means when they are acting as a base, then this proton will attach on O minus. So there is no possible other structure of this form when it is acting as a base. But when I am removing a proton from this, it will form this structure, and in this case this negative charge can delocalized over the molecule, and in this way it is exist in more than one form. So when the charge is delocalized, the structure is more stable, means the conjugate base formed is more stable. Therefore amides are weak base and they are good acid as compared to their basic nature. They are acidic in nature. Next is, if I remove this CO group from the amide and place a CNH group, then the structure will form is known as amidine. And if I provide a proton to the system, means when it is acting as a base, then this proton can attach on this NH group, and the structure form is further stabilized by delocalization. The lone pair of electron present on nitrogen can delocalized over the structure, means the conjugate acid form is stable in nature, means amidine are stronger base as compared to amines, because their conjugate acids form are stable in nature. So always find out what are the conjugate acids and bases, and then determine their stability. Then you will get the correct answer. Next is the compound when we have 3 NH, 2 NH2 and 1 NH group at carbon. It is known as guanidine. And when we provide a proton to the system, means it is acting as a base, it is accepting proton, then what will happen? Because the lone pair of electron present on nitrogen can delocalized, so the proton can easily attach with the molecule, and this molecule, this conjugate acid is highly stable in nature because it has 3 form of delocalization. This positive charge, the lone pair of electron present on nitrogen can delocalized over the structure, so this structure is very stable in nature. So guanidine are highly basic in nature. They are very strong base. So that's it. I will end my today's video here. Thank you so much for watching my videos. Please subscribe to my channel and press the bell icon for future notifications. Share it with your friends. Thank you.